Hi everybody, this is Roberto Fodera and I'm presenting the project findings for the Managing Machine Learning Project course. Let's start now with the opportunity evaluation and spend some words about the problem itself. So typically, CO2 sensors tend to drift due to several technical factors. Those CO2 sensors, air quality sensors, are primarily used for demand control ventilation in HVAC application. So is there now a problem? And yet it is a problem because large drifts offsets value lead to increase energy demand cost, reduce lifetime of the product itself, and or lower comfort. Can machine learning help solve this kind of problem? Yes, it can, because it can predict offset drift value over time based on past data collection and eventually propose and or automatically correct them throughout the whole measurement range. Further, it can propose when a manually calibrated is needed and or an exchange of the unit itself is necessary. And the people, of course, who cares are typically building owners, HV installers, also renter, and every person in the building, because everything is comfort and of course cost related. Now let's go now a step further with the CRISP and business understanding by defining the problem, defining success, and by identifying potentially relevant factors. Let's start now first by defining the problem. So the target user are HVAC systems provided for buildings, houses, stores, and etc. The problem itself is the CO2 drift compensation, which needs to be prevented and corrected on a regular basis. Why it matters? It's very clear, it was said before, because it increases energy demand cost and lowers comfort. And the current state is at the moment that no compensation is done, or some manually easy one-point calibration once in a while. Success factors: expected impact, improved accuracy and control loops, energy cost reduction. Output metrics can be defined in energy savings by a certain amount of dollar per month or year, and the output metrics can be defined by MSE predictions by a certain amount of value. And further identify potential relevant factors are clearly the application itself, that means the installation place, the environment, but also temperature, humidity, pressure, time, and the CO2 technology which is used at the moment. Let's have now a look at the solution validation by shortly describe of the solution concept. Here we would like to create a machine learning model that automatically calculates the drift value, in this case the output, based on different features, in this case temperature, humidity, pressure, etc., and adjust the output measurement value, in this case the CO2 ppm value. Now, what is the validation of the proposed solution concept? On the left side, you can see the process, and on the right side, I just added some remarks specifically for the project itself. Firstly, of course, we start with evaluation to evaluate the data accessibility and quality. In our special case, that means we collect data of an already installed building or buildings with the appropriate sensors. If necessary, we have to enhance it with additional sensors which are not available, or we can use a new project as a test environment and add all the sensors which are necessary and collect, of course, the data. Next is validate and identify the optical machine model. And in this case, I have to say that based on already available information, a multiple regression model may be at first the right approach here. After that, we assess the model, generalizability, in short, evaluate accuracy, precision, etc. And after that, when we are satisfied, we go and verify the performance in the real world and test the machine learning model. If the results are okay, then we finish. If not, we go back to point number 2 and start to validate and define the next machine learning model, and again and go through the whole process again. Let's now have a look at the machine learning system design decision. First, cloud versus edge system. Here, this depends on the decision on how the problem should be solved and how data will be collected and used. That will be used as a reference. Like outside values, reference sensors values may also influence the decision. Based on today's information, CO2 is a sluggish measurement parameter. That means that the prediction and therefore the correction should be sufficient after a longer period. That means weeks or months. To do this assumption, an edge solution to start may be more appropriate. A cloud solution may be considered on a later stage. Second, offline versus online learning. As already described in 1, due to the characteristics of the parameter, an offline learning model training will be the right choice here. And third, batch versus online predictions. Again, here very clearly, both prediction may be appropriate. This needs to be verified, tested during the project based on the characteristics of the measure parameter already described above. Right now, the prediction should be generated in batch. Finally, the potential risk in production. Very clearly, factors which may additionally influence the output and therefore the model and or the measurement value due to usage of the buildings may be disinfections, hospitals, or chemicals, in example, laboratories. All these may clearly influence the output and to reevaluate the whole model. Now, therefore, I've finished my presentation. Thank you and have a nice day.